I was just, yeah, I wanted to activate to make sure it was working. Right. Yes.
So we can have your attention for just a second, please. On Thursday, there is a dinner at night. Then like the protocol it just for vegetarian and vegan options. If you can just answer it, that would be very nice. Thank you. Yeah.
Well, hello everyone. Nice to be here at the summer school. First time for me. I'll be talking about Julia Geo, and actually most of this presentation just about Julia, just about trying to introduce it with Jupyter notebooks. I'm doing this without a microphone, so in the back, if I'm inaudible or you cannot read something, let me know. You can make it bigger, and you can also run the Jupyter notebook yourself, or actually join Zoom. Maybe a few people can join Zoom, and then you have a zoomed-in version of my screen here. So let's start. I called it a gentle introduction. I actually wanted to go die hard into Julia Geo, but since many of you are, well, not that familiar, we start off a little bit easier. Normally, I would give this presentation together with Martijn Visser, who unfortunately could not be here today. So it's just me for today. Normally, I explain that we're two really different people and that the pronunciation is on my double A, Maarten, and the other guy with an IG. We're both researchers at Deltaris, and part of our research work, we develop open source software. And sometimes this is part of our work, but also sometimes, well, my time, during the weekends, we develop some more packages. And we've been using Julia for, I think, the past 5 years. And it started out just like you are now, like, what is it? How does this work? And after these few years, we're now also seriously developing packages. And we're trying to build the geospatial stack. So today, a little bit about setup by Julia, and then Julia, to get it working in Jupyter. And then I have several Jupyter notebooks to go through, which is first an introduction, a bit about package management. Then we have to see where we have time and how long everything takes. And eventually, I also want to talk about the geospatial stack at the end. But it all depends on the speed. And if something isn't clear, please interrupt me. We can discuss it at length. Jupyter notebooks are for changing things and quickly iterating. So yeah. Then a little note about tomorrow. Because Martijn is not here, we don't have a whole session planned for tomorrow. That's tomorrow morning. I'm not sure in which room. But let's say we keep it a non-recorded session tomorrow morning. I will just be there. We can discuss about Julia. We can do interactive things. I can help you with your installation, or whatever you fancy. Okay. Let's start the first notebook. Well, maybe first the question, who got Julia installed? That's, well, apart from those three at the back, the rest have got Julia installed. And is it also working? Did you install a few packages? You got Jupyter notebook working? No. Okay. Well, no-ish. Well, feel free to move to some neighbors who have it installed or have it working, then you can join them. In the end, I can maybe help you if you have some errors on your local computer. This is a MacBook, so what works on Mac might also work on Windows. I have also a virtual machine with Windows. So I also got it working, this notebook specifically. This is the notebook that was also discussed in the summer school installation. Wait. Yes. So there's the Google Docs about the for the summer school with the installation manual. I've updated this. And this worked for me also on Windows. So I've got Microsoft Edge browser here, in which I have the example working. So should work. Let's start with the first Python notebook. I put everything on GitHub. I shared a link in Mattermost. And then we do intro. Intro, yes. So, Julia, there were some guys back in 2009 at MIT. And they thought of a new language, and they were really greedy. So they wanted everything. So they made this manifesto that they wanted something as simple as Python, but with the speed of C or C++. I'd say they largely succeeded. Of course, there's enough to still improve, but that was back in 2009. They started developing the language. So this is Jeff, Stephen, Carol, and Alan. And they make the first release in 2012. And back in 2018, we got the first 1.0 release. So the first, let's say, mature version that's stable and backwards compatible for the future. And currently, I think a week and a half ago, they released version 1.8. So the big takeaway here is it's only 10 years old. And Python was invented in Amsterdam, I believe, around the time that I was born. R came, I believe, roughly 2 years later. So Julia is like 20 years younger than the languages you're already used to. And of course, that means maybe more bugs, smaller ecosystem, everything's slightly less mature, but we've got great examples in Python, in R, and of course, GDO, GeoS Proj, all the packages that we can already build on. So there's certainly something there. And it's taking off, I'd say. It's all developed on GitHub, the whole language. We're talking about, what is it, 50,000 commits, 40K stars. It's growing, and it's wildly popular, especially for scientific computing, machine learning, that kind of stuff. So let's dive into a few of the features. And I will tell you something about them via these examples. So you create a function using the function keyword. It has a name, and it takes some arguments. And I'm sure this is quite familiar to you all, because in Python and R, you do roughly the same things. And this is, well, we can call it a power function. And this is what it does. Note here that we put a triple quoted string on top of it, just before the function, and that's the docstring. So in Python, you would actually put the docstring here on the first line after the function, which would be def. In Julia, it's on top of it. And if you indent the first line, it's actually a code example as how to call this function. And we can do the same a second time. And this is special about Julia. What you might not be used to is that we can again call this thing power. Again, the same name. And now we give it different arguments. We actually annotate the arguments A and B and say, look, these are integer typed. So now, and then you could, in that function, you could do something special for integers. Of course, that's not necessary here, and it's the same code. And if we compile this, well, you just get the function back. And now, just I think like Python, we can type a question mark and then a function name, and then we get the help. And now we got two help definitions. The first with the small string, and then one for integer versions. So this is multiple dispatch, and this is at the core of the Julia language, that you can have multiple methods, and depending on your function arguments, Julia chooses the correct function. So this makes some really nice things possible, to which I can look back later. And now you should know how to write functions. Yeah.
Can you use code a little bit?
Yeah, sure.
Where does this text come from? What is power is it real?
This, sorry, again, what
Search, power mod.
The question mark.
I know, yeah, after the question mark.
Right. So this is a suggestion by Julia itself. saying you search for POW, but there's also power mod is POW2. So these are the other functions available currently. So if I would make a typo, probably, then you get a nice error message and it gives those suggestions. So that helps. Okay, any other questions already? I talked about multiple dispatch right now, that you can have multiple methods for different arguments. And this goes also for methods in the base language. So we can make an object like you have in Python. And we're going to call it my measurement, which is, well, a measurement with a certain error statistic attached to it. So in Julia, that's called a struct. In Python, you probably know this as an object. In R, I actually don't know what the definition would be. This is how you create it. And then we can say in base, you've got the multiplication method, the star. So this is normally 1 times 1 is 1. And now we can actually define this. So this is something in the base language itself. We can define this for our new struct called my measurement. And then can we say you multiply by some other number. And that's basically my measurement. And you can create a constructor that it takes the multiplication also to the error inside the struct. And if you then create my measurement and multiply it by 2, you see you don't get an error. And the error value of the my measurement itself is also multiplied by 2. So you can basically extend the base language for all your own special objects that you want to create. So I often make custom point types because I work with point clouds. And I can use many other packages and they don't know about my own custom point method or my measurement. But since we define some base interface functions, everything talks to each other. So this is a really powerful construct. And we'll see it again and again in the language. Okay, some other features which you might or might not be interested in. You can call C libraries, like the C library of the system itself. So there's a clock function built in each OS, and I can actually easily get the seconds back since the Linux epoch. So you can interface with C libraries and also Fortran libraries. If you think, is this interesting for you or relevant? Well, GDAL is a C library. So we're calling GDAL in this way, although we make it a little bit easier for you. One feature of the language in Julia, which I really like, is emoji support. I don't advise coding too much with emojis. It pisses other people off. But emojis is a joke. But there are some useful things to Unicode because it basically has Unicode support. I know Python has it as well, but I don't see it often used in coding itself. For scientific coding, it's really useful if you can use Unicodes because you can define the Greek alphabet. So if you want to code with density, you type in backspace rho for the Greek letter, then you do tab for an autocomplete, and now I have the Greek letter. And so I can compute with these things. And the same goes for pi. Well, there's a huge library in there. So it means if you type over an algorithm from a paper and it uses all these symbols, you can just use the same symbols. You can define them. Rho probably doesn't have a value. So this should error. See, and I can assign rho just a value. And now I have a density defined. I think this makes scientific code much more readable. So I advise to use that and maybe not use the emojis. So from Python, you probably know that if you write long for loops or nested for loops, that it can become really slow and that you have to vectorize things, or especially NumPy. For Julia, that's not basically the case. There are certainly differences between different ways of writing your functions, but if we implement the Riemann zeta function, basically, if we want to find pi with a certain algorithm, you can write it just with a for loop. So we're writing a for loop over 100 million here. And compare that to writing a vectorized notation, where we basically use a dot. So here we use a dotted notation, and this is broadcasting. So what this does is it's an element-wise operation. So if we use a dot before the division operator, or use a dot between the multiplication operator right here, it's element-wise, which means it's not one divided by the array, which would yield an error. It's one divided by each element of the array. So if the array is 1, 2, 3, it's 1 times divided by 1, 1 divided by 2, 1 divided by 3. And if you run these different typed versions, you see that they're really comparable. Well, the vectorized function is actually 5 times quicker, but they're still both quite fast. What I meant with the broadcast support is if we say A is 1, 2, 3, now I have a array, a vector specifically. If I divide that array by 1, I should get an error. I don't, crap. If I type it longer, I should get an error, no? This is always, don't improvise on your own presentation. Okay, for other arrays, no, this will probably work as well. Anyway, you can use dots to do element-wise operations. Yeah, let's move on. Any questions thus far, apart from my mistakes just there? Okay, a little bit about arrays. I just touched upon them, and sometimes the need to broadcast over arrays. In Python, you really need NumPy to do matrix operation, arrays, vectors, because in Python itself, you basically have a list, and that's really not, well, I don't think it's good enough for scientific computing. Julia was built for scientific computing, so it has arrays built in. So basically all the functions that you normally know from NumPy, they're built in the language. So you can just make a random array by calling rand. So this would give you a one-dimensional vector of length 5. You have the function 1, so that's it. That would be a 3-dimensional array with these dimensions. You can also initialize a whole matrix like this, and then it's basically it only allocates the memory without setting any value. So C here with you get undefined here. So you need to set the values. It's only reserved in memory. And here you see a broadcast example again. So 2 vectors, if you multiply them by one another, it does the 1 by 1, 2 times 2, 3 times 3, until 5 by 5. So that's a nice broadcast operation over 2 vectors. And this is all built in the language. Yeah, some other features. I don't think I'm going to talk about meta programming. Who does meta programming and macros in other languages?
Well,
well, that's it.
pretty soon, yeah.
Okay.
Yeah, it's extremely useful. Yeah.
I agree it is, but if no one, I'm not going to explain whole meta programming here. Basically, if you type in code, it's basically a string. So Julia and Python and all other languages, they need to figure out what you typed. And they figure out this is a number, this is operation, this is another number. And in Julia, you have access to that intermediate language, which means if you write a function, you can write a macro in front of it, and you can edit that function. So you can make thousands of variants of that one function automatically. So in this example, if you have a Julia source file and there is 1 plus 1, you can call meta.parse. And what you get, you see it as an expression. And you can start editing this expression by these arguments. You can construct these expressions yourself. Basically, all source files in Julia, there's another level to them, and you can edit them, generate them. ask me later. I'll give you some examples of how I used this in the past, but it can save you a lot of time if you use this right. So now a really interesting thing about Julia is because it's so new, it could take a good look at all the existing languages and pick the nice things of those languages. I mean, it's cheating, and another language in the future will do the exact same thing. I'll take the good bits of Julia. But they have a very nice built-in package manager. So I know Python didn't do that in the beginning. So there's pip, but it's a bit external. Then Conda came to save things or change things. Now we're moving back to pip because pip has binary packages as well. It seems to be working sometimes. So this is also inspired, I think, by the Rust package manager, another nice language. So just like I showed you before, you have the question mark that you can put at the beginning. You can also put a bracket, a square bracket close in the beginning, and then you get into package mode. And here I do ST, and that's short for status. And then it tells me, look, you're now in a project. There's a certain project activated. And this is my main environment in Julia. If I start Julia, this is the environment I have. And it tells me about all the packages I have installed, which are, well, they're quite something. They have a unique ID, and they tell me about the version. So in the package manager, built in, there are environments. So I can change environments just like you use Conda environments or use pipenv. R also has environments from the top of my head, but I don't know how to work. And if you want help about the package environment, and you probably used it already to install some packages, otherwise you cannot have the notebook running. If you want to know more about it, you can type a question mark after the bracket, and then you get in, well, they have a nice help page. These commands work in Jupyter Notebook, but they work just as well in the replicator, which is on the command line. I will make this even bigger. If I type the bracket in the replicator, I don't see it, but it changes to the blue and it says package. Same with the question mark, and then it turns into help. Sorry, it's all the way to the left down. Let's go back to the Jupyter Notebook. That's a bit more readable. So this is the end actually of the code part of the intro notebook. There are some interesting projects to look at. I think most interesting for us is that the Climate Modeling Alliance took a decision a few years back to make their new model that should, well, simulate the whole climate and climate change. They chose Julia to do that. And well, they've been developing ever since. It's quite a nice project. Our reason, so mine and Martijn's, to use Julia at Deltaris, a research institute where we work, was basically, Martijn is a hydrologist. He worked with a lot of point clouds. We use that for elevation modeling, and then we can simulate floods. So it's about flood protection. And we got a large point cloud with elevation measurements, and we wanted to process that with, well, we read a nice paper, and we wanted to implement the paper on that point cloud. And Martijn knew Python, but Python turned out just to be way too slow. And then the question is, what do you do? You can go to maybe a software department and, well, let someone else do it, but that's not always an option, or can be a very expensive option. I think the good option, or the reasonable option back then, would have been go to C++. There's Poodle, also a very great open source package to use for point clouds. But it's a step too far for, I think, most of us. I don't like C++ programming myself. And Julia fills this gap, this two language problem gap, that you want something easy to write like Python, R, or MATLAB even, maybe not MATLAB. But if you want to get it sped up or have some problems, you probably need to take a look at another language. And Julia tries to solve that you don't have to switch that language. And that worked for us. But very big, well, exclamation mark, it worked for us. If you don't need this, don't switch to Julia. If you're happy with Python and you have it working for your stack, please keep your stack. If you're using R and you're happy, keep using R. This is just another language, and I'm trying to build up the geospatial stack to make it just as useful as Python and R are now. I put a few exercises underneath these notebooks. We're not going to do them now, but you can do them in your own free time later. And maybe come back tomorrow and ask me questions about the exercises if it doesn't work out. So let's get some water, and then we switch to the, I think the package manager notebook. This should be a short one. I'm already spending 25 minutes. We're going to skip some things later on. Can anyone tell me if there are questions on Mattermost or Zoom? No, all quiet. Oh, good. Julia Package Manager. I already showed this to you just now, but I want to go through it for the ones who didn't see it completely. You can add packages in the language itself, and you do that with the add command with the bracket. If you're in a script, you cannot do that bracket thing. You have to do using package. This is also how you use a package, and then you can do package add. And that would be Unicode plots. That was the example. And you see it says resolving package versions. It downloads the general registry of all the packages automatically. It will update a local environment for me. And it will tell me about all the updates it did and packages that it added for me. So that's a lot of packages. Note though that I think half of the packages you see here are built in. Well, these ones aren't. But some are built in, and there are also in a separate namespace inside the language. And then it says at the end, it says pre-compiling. So what that does is Julia is, I think just like Python, if you type in something, it compiles on the fly. Well, if you have C or C++, you need to compile everything, and then you have a useful executable that you can use. This is interactive, and it means that the first time you run a function, it's slow because it's compiling. And after it's compiled once for the specific types, then it should be fast. If it's not, we probably did something wrong. And Julia tries to pre-compile all the packages you downloaded first. And it can do that for most of the methods that the packages define themselves for their own types, for base types, let's say. It cannot pre-compile for your custom things that you're going to put in the package. So there will still be some slowdowns in the beginning, and you see that especially with plots. Plots is probably, well, plotting in the beginning is quite slow, and after that it's fast. If you want to use a package, you say using and then the package name. And that means it everything that the package exports, it's now available. So if you do using Unicode plots exports histogram, and that's why we can call histogram here. You can also do import Unicode plots, and then it doesn't make the names of the package available in your namespace. You probably, same with Python, you can import as, don't do the wildcard thing. So, because you want to have your script, you don't want to have too many symbols around that could clash with your own variable names. You can also do import as, well, IP is maybe a weird acronym, but it helps sometimes to make acronyms for package names. Because in the Julia world, we really like to have long names, descriptive names for packages. So sometimes they're really long to type, and then it's useful to shorten them by up. Let's go back here. Well, this is a simple example of a histogram. The nice thing about this histogram and Unicode plots is that it works in your terminal. So you can do a little plot in your terminal, all with Unicode. It's a good way to explore some data. And this is just a random sample. in terms of time, I will skip the activate a specific environment that you can create. But what I want to say about it is that if you have an environment created, a certain two files are made. A project.toml. Toml is I'd say a readable INI format if you are unfamiliar with it. And there's a manifest. And in the project, it defines your dependencies. So in this project, it's an environment definition. There's the example package and the GDAL package with their unique identifiers to find them. And the nice thing here, and I think Jakob, I'm not sure if he's here. Well, aha, you are. There's a manifest.toml, and it's a machine generated file. You shouldn't touch it or edit it, but it records the exact versions and the exact hashes of the packages used. So this is the reproducibility thing. So if you share a manifest with someone, they can download the exact same versions of the packages that you've had there locally. So this should be perfect reproducibility. And you see it's also much longer because it prints all the hashes. It can actually tell you the hash of the Git tree because Julia uses often Git for the package management. And it can link to GitHub and use that as a package. And it records all the dependencies of your dependencies as well. So I downloaded GDAL, which you see in the project.toml on top. But GDAL itself has dependencies on C, num, GDAL.gll, network options, and proj. So these are recorded as well. And you see that this GDAL.gll has its own dependencies. So this manifest is recursive and it's quite big. But it works. So this is really good for reproducibility. Then the one thing I really like, is binary packages. And you just saw them actually. We saw the GDAL here as well, geos.gll. It's a normal package, but with this _JOL, it indicates that it's a binary package. It's basically built automatically. And what we try the same thing as Anaconda does for Python. Basically compiling all the hard to compile stuff like GDAL, like geos, and proj. We do cross-compiling and we link them all together. So the nice thing here is that also you on Windows, Linux, even exotic Linuxes, although then it's fingers crossed, you can just do add GDAL. I hope you already tried that. Of course, this has already resolved. And we can say test GDAL. This is still in package mode. And now we're testing GDAL. And basically what we can see here, it's running the whole test suite of that GDAL package. So I just showed you how you can run tests for a specific package that you downloaded. But what you also see is that this is actually working. It found GDAL drivers. So what Julia did here is download the package, and there's a complete working GDAL C library compiled for your own system. And it works. So people behind the screens are working very hard to keep this running. And like you know from Conda, sometimes things break, but we try to keep it hidden. Yeah, that's it.
So is this dependent on dynamic libraries on your system, or is this all statically linked? Are these static libraries?
This is all linked together with the specific Julia dependencies as well. So it shouldn't be statically linked. And it can clash with your system libraries if something is missing, or it depends on the load path of the Julia when you start Julia.
But if I update my GDAL installation,
it should be completely clear from that.
It's
yeah,
independent.
it should be completely separate.
Okay.
I have a question.
Yeah, sure.
I just tried it here and I took their hub, and then the point is that add will try to put the software in a directory I can't access. Is there a way to put it in a user space? That's some
Wait.
sort of local installation.
What is the exact error that you get?
It basically tries to put the package into the path that I can't access.
Ah, it's a permission thing
Yeah.
because you're remote. Okay. I'll have to come back to you for that. I think it's possible to set the dir where you save all the packages to make sure it comes into a user writable directory, but that's probably a startup option for Julia. So if you're already here, it's probably too late. Although, but Julia works, so you got the base thing working, and you can add some packages, or you can add.
I can't add anything.
Yeah, okay. Yeah. Any other questions? I think the air code just started. Okay, it was a bit hot. Sure. In favor of time, I'm gonna skip developing the package, but again, you can basically do that from the package manager itself as well. Then you have a template for a package. So I think I have, this is a 1.5 hour session, right? So I have like an hour-ish, small hour left. Well, let's skip the differences with Python, because I think most of you are also used to R. I think the main difference with Python is Julia uses one-based indexing, just like you do in R and in Fortran. So if you're used to C or Python, you can be surprised. That's one thing to watch out for. But otherwise, I will leave it at that. I'll now go to the parallel computing notebook, so you can open that one as well. So Julia has built-in support for threading and parallel processing. So it's basically running things in parallel within the same memory or distributed over multiple processes or even computers. And that's really useful, especially if you're used to scientific computing, because models are always slower and bigger than you thought they would be. So if you want to speed things up and have a nice computer or workstation, knowing these tools is really useful. And I will give you some examples for both threading and parallel processing. Who's familiar with parallelization in your code? See one hand, each hand. Okay. Interrupt me when you lose the plot. I will try to take it slow. So threading is basically doing multiple things in a thread within the same memory. So Julia like this is one process. All the variables that there are. If you use threads, you can access the same variables within the same session. So I started Julia with a startup option. So I will always have 8 threads available to run. And that means that if I use a built-in library called threads, and I make a for loop. So let's say I'll create an array right here, filled with zeros. And it's twice the length of the number of threads I have available. So this is a vector of the length 16. And then I create a loop. So the loop is the same as you've seen before. Basically, it's a for loop. Length A is maybe, well, you shouldn't code it like this, but it works. So this would be a normal for loop if you do something here, and it would fill in 1 in each element of the array, right? That's sensible. If we use threads, we basically split this task, this for loop, which is basically 16 individual tasks. We split that over 8 threads. And your CPU will basically do the work and do that because I have 8 threads, hopefully 8 times in parallel. So that should be theoretically a speed up of 8, which would be great for any model. Of course, there's always overhead, and probably, I'm not sure about your laptops, but Maybe there are not 8 threads available even on the system, but less. So there are all things going on. You use a add threads macro in front of the for loop, and then it's basically multi-threaded. And we demonstrate that here by in the for loop, instead of setting it to a 1, we set a thread ID into the array. And if we execute that, you see that the array is now filled with numbers, 1 to 8 actually, but you also see it's not specifically in order. So threading happens all over the place. It depends maybe on which thread is less active. So we see it started with 1 and then 6. And you also see it's because it has length 16 and there were 8 threads available. All threads nicely got 2 tasks to work with. So this is built-in threading. If you have some larger arrays to work with or some large computations, this is really useful to speed things up.
How do you make more threads available?
It's a startup option to define how many threads, but it really depends on your system. Basically, you want to, if you have hyper-threading on your system, it's basically number of cores times 2, often like that. It depends on the system. That's probably the number you should aim for. Otherwise, it just gets more things trying to put on the same CPU that's already cramped, and you get overhead and slowdowns. So it really depends on your CPU, I'd say.
Which you customize. Once I know how many threads I have available, customize it. I need to use a startup option.
I believe so, yes. Because I put it here. I'll come back to that later and we'll answer it. I'm going to write these things down now. User dir. Okay, a warning though about threading, because this is yeah, a warning about threading. Each thread basically doesn't know about what the other threads are doing. It's basically running on its own, going full steam ahead, and this can create errors. And we see that here by doing a simple sum over, well, with threads. So we start with a total of 0. Then we create a threaded loop of 10,000. And we basically add 1 to the total. And normally, if you do this without threads, you get 10,000. Logical, right? If we do it with threads, we get 1637. So this is clearly wrong. And what happens is if you do the plus is, that's by the way notation for total is total plus 1. If you want to add 1 to something, you need to check what something is. So one thread does that, sees 5, adds 1 to it, and writes down 6. But in the meantime, some other threads already saw the same thing, also added their number, and it basically invalidated the whole state. So this is called a race condition, and they all try to modify this value at the same time, and they're basically updating it with old values. And sometimes this happens. For example, 100 works. Apparently, this is maybe the scheduler in Julia or so noticed this works fine. 1,000 sometimes goes right, and sometimes it doesn't. See, it really depends on the state. It's quite random. Now it's stable. Stable-ish. So threads are dangerous. Also because most C libraries that you call, if you want to call C libraries like GDOL, they don't like threading at all, because you can update pointers and you basically invalidate the state of some library. So you can crash Julia with this if you call into C libraries that are not threaded. So there's I'd say a warning sign here, but if you use purely Julia code, this should be fine and it's great to use. There's a fix for this, but I'm gonna skip it. It's use atomic. You can find that in the manual. So the other thing for parallel processing is using distributed. It's a built-in package called distributed. And you can basically say add processes to, and then you get the IDs back of those two processes. So normally if you say Julia in the command line or Jupyter, a process in your system is started, that's called Julia or Jupyter. And there's one such process running. If you then add this, add process, two child processes are started on your system. So if you look into your task manager, you should see that as child processes. The nice things here is that another process can run another job. And if you have multiple CPU cores, again, your Windows or your OS will divide the work over those cores. So this is not threading, and it's probably if your CPU is hyper-threading, it's basically Julia decides how threads run because it has full control over them and how it divides over some work. Well, using processes, you leave much more up to the CPU and the system. But the nice thing is that if you work with distributed, it could also work for a cluster of multiple computers. It basically doesn't matter. There is a process somewhere else that you need to communicate with, and it runs stuff for you. There's, however, a drawback. And I'll show you why. Do we need shared arrays? So what's happening here is I will comment out this code because otherwise we don't get it. This should be. What did I do? I'm sorry, I'm improvising again, and I should have done that. Basically, if you use distributed code, you start a new process, and a new process has its own memory. So all the variables that you defined before, they don't live in the new process. So again, you can edit a for loop, and instead of putting threads for it, you can use add distributed. And distributed automatically will make copies of the variable of A. So it can actually read them. That works fine. But in the end, why does this work? Sorry, this keeps working while it shouldn't work. In essence, if you give a task to all your child processes, they will do the work, but on their own variables, on their own copies. So on the main process, and we're in the main process here, you will normally never see those results. So whereby threads, you need to think about race conditions. With distributed, you need to think about where are my variables and how do I synchronize them over these processes. Same if you are on a cluster and you have multiple machines running, they also need to talk to each other and sync up their state. So I have a cell here, and I got a comment back from Martijn Visser that his computer almost crashed. So I hope you didn't execute the cell yet, because maybe we should put, no, I will do 100, but I will show you why. So we add here our 100 processes, and we're going to run on 100 processes, even though I don't have 100 CPU cores available. So I will really overload my system. And then we're going to define a new function, and we call it slow task, because distributed processing is really useful for slower tasks, long-running tasks. So we mimic that not by a really difficult function, but we're just going to sleep for 5 minutes, 5 seconds, sorry. That's the function we'll run. Then we'll make an array of 100 items. And then we're going to run this function, slow task, on each of those 100 items. So normally, if you do this, it's 100 times 5 seconds. So we should be waiting, serialized, we should be waiting 500 seconds. I hope we don't do that. But if you use pmap, this is from the distributed package, it will actually divide that work over those 100 processes. And I'm not going to execute this again, otherwise I will add another 100 processes to my system. But what you can see here, I timed this. with the use @time macro. It's built in. And this takes 5 seconds. So it should be 100 times 5 if you serialize this, but using distributed, it's 5 seconds plus a little bit of overhead because, well, things need to happen. There needs to be communication. So this is again a way of speeding things up considerably. And because, again, don't do this at home with 100 processes. It's basically sleeping. So it could do multiple things on my system, 100 processes like this. But if this would be a heavy function, you really crash your computer. Okay, always good to execute the last one. Remove all the processes that we've added. Cleaning up, basically. That's a short intro to parallel processing in Julia. Basically built in. I see a lot of people, well, staring a bit. Is it still clear? Are you still following? Is it still fun? Okay, I see some nodding heads. That's good. Great, thank you. Do you guys want a small break, or do we continue with, I think, the last notebook? Let's move on. Move on. I see. Yeah, quicker. Oh. Okay, then open the Geo the Geo one. It's called Julia Geo.ipnb. So this is finally about the geospatial stack. This is why we're here. But I basically need to introduce a lot about Julia itself first. As I put in this header, I actually asked Martijn, am I not too negative? He mostly said, well, we're lagging 20 years behind in Python and R, because they're great examples. We can catch up a little bit quicker, and we can build on GLs and GDOL. So it's already useful, and we use it in production all the time. So Julia Geo is actually a GitHub organization. It's basically just an org in which we try to collect all the geospatial packages in Julia and then make sure that they're updated. So it's for maintenance. And we aim to try to connect them a bit. So if you have geometry in one package, another package should hopefully understand that random geometry. So that's our aim. Basically connect all the geospatial packages in Julia. We also have a website, I linked to it, and we also did a few presentations, one at FOSS4G all the way back in 2019. And more recently, one at JuliaCon, which is the Julia conference. It's online. And in this example, this notebook, I'm going to use, well, I think also Rasters, actually. Rasters, like this. This is loaded for me. So I'm using Geodata Frames, Rasters, GeoArrays, well-known geometry. Let's change this for Geo Interface. Geo Interface. So like this. Okay, hopefully this works. So Geodata Frames, that's data frames, you know that from pandas. It's like tables. So this would be the GeoPandas equivalent in Julia. Rasters is a package for working with rasters with actually multidimensional data. So it would also work for NetCDFs. So it's like, I'd say X-ray, or it's not yet there maybe, but that's what it mimics. GeoArray is much more simple. It's still rasters, but only the normal GDO ones, let's say. So it's like Rasta.io in Python. Geo Interface I will come back to later, but it's basically an interface for vector data. Well, downloads and plots, they should be self-explanatory. Disclaimer, by the way, I wrote Geodata Frames and GeoArrays, and that's probably why they're in here. There are more packages, but I'm just more familiar with these. And also, in terms of, I wrote these packages, I'm building on ArchGDOL, which is built on GDOL itself. So actually, I think it's even and the famous GDOL guys, which we also need to thank here, because we're building on top of a lot of other packages. So let's start with the raster. So we download the geospatial raster. I use a GitHub URL here. from Gieschen. He wrote the ArcGDO package. It's like a Julian package for talking to GDO, just like you have GDO in Python. And we download a small TIFF file. So we can use the downloads package. It's built in to automatically download from that URL, and it will download it to temporary location. And we store it as, well, Raster FM, Raster file name. And then we use the GeoArrays package to basically read that. And what we get back, it's a bit unreadable. Maybe I should make an issue about this. Is we get back an array with an defined map, which is basically a coordinate transformation. And it's a definition beyond that of the coordinate reference system. In this sense, it's looks like a well-known text to me. So we can see that if we put that in the GeoArray, the GA variable. So if we access the array, we see it's a 100 by 100 by 1. And the last dimension, the 1 is actually the bends of the array. We see it's uint 8. So it's an unsigned integer. And we have all these values that we can access. And this is a normal built-in Julia array now. So we can do all normal array operations with it. Then we have the affine map stored, just like Raster IO actually makes a affine available to use coordinates. Basically, we have a raster that's placed somewhere in the world. So we need to know how the logical indices of the array map to coordinates in the real world. And we need to know the coordinate reference system. And this time it's indeed well-known text. And it's in Americas. So we can use plot because we loaded plots all the way on top here. And note that I just call plot. So this is the plots package. And if you just say using plots, it will try to determine the most optimal plotting library on your OS. So for Windows, that would be a different one than on Mac or on Linux. And then it just plots GeoArrays. And this because I made a recipe in my GeoArrays package to determine how this should be plotted. I basically defined that an array should be a heat map. So if I use plots checks my package, sees that it should be a heat map, and then it can plot one. So we have a nice visualization of this thing. I actually don't know what this thing is. It's one of the test raster files of the ArcGDO package. But this is very quickly how you basically download and read a raster in Julia, including the geospatial information, because you see the plot also has the coordinates defined. And this also works for subsetting. So we can, with array notation, we can basically say, instead of this 100 by 100 raster, I will take only 2 to 50 of the x coordinates and 2 to 50 of the y coordinates. And then we get a 49 by 49 GeoArray. Actually, with offsetted coordinates, so it actually still aligns to the correct position in the world. And very similar again to Raster IO, we can request the coordinates of a point in my raster. So that's the first cell has a certain coordinate. And we can also do the inverse and ask the logical indices. So which cell would be this coordinate. And then you get back 1, 1. I'm happy that this matches up. Okay, that's it for GeoArrays. So simple, raster manipulation package. It's built on ArcGDO, which is built on GDO. So this is basically, it can open any raster that GDO supports. The GDO package in Julia, which has a lot of drivers, but probably not all of them. I also want to show rasters. Very similar, but also, like I said, made for NetCDF and much more dimensional data. So you basically call Raster on the file name, and you get a Raster object back. And again, it's very similar. You can see the same data, but Raster is much more explicitly tells you about the dimensions of this array. So it really says X, Y, and then band with a certain range of these dimensions as well. And you can use the following notation to subset this. So in this notation, you really need to tell which dimension do you want to subset. So this is X coordinate, well, this one to a higher one. But it would mean for NetCDF, for example, if you have NetCDF with a time dimension, you would do time and then maybe between start and stop. So this notation works also in much higher dimensions. So the Rasters package is, I say, a bit bigger, and it can also do zonal statistics, masking, rasterization of vector data. So if you're into that kind of thing, use Rasters and you can skip GeoArrays. That's it in terms of Rasters. So let's take a look at, well, the vector dataset. It's also always the big competition, whether you want to use the vectors or Rasters. So this is, we're using Geodata Frames here, and that's was inspired by GeoPandas. And GeoPandas has really fancy stuff, and they're improving all the time. Esther just told me about new plans in GeoPandas and how they're improving. I think they're now also doing parallel processing for geospatial operations. We're not there yet. We're trying to get a spatial index working nicely in our tables. But what we can do is load and write data and use the rest of the Julia ecosystem. So just like the Rasters, we can download a file, and this time it's it's actually used in the challenge that you guys have. It's a geo package from the spatial prediction email dataset. We download it, and again, we call read from data frames, and we get a data frame back. So a data frame, it's one of the more popular packages in Julia. It's basically like pandas. It's the pandas equivalent. I think it's even faster. And the only difference is, so this is not a geospatial data frame. It's just a data frame. With the only difference is that the column here, the first column, it's of type iGeometry, which you get back from GDAL. So that's the spatial column. There are no further definitions, and it's just a data frame like that. And you can access these columns with the same notation as arrays, and actually very familiar to pandas. So if we want to plot this, we do need to filter some data, because I saw there's loads of missing data in these training data sets. So data mangling is, of course, always the larger part of all the analysis that you need to do. So here we filter the whole data frame with the following command. So basically filter the row if the month is not missing. So we call is missing, and we inverse that with the exclamation mark. So we only keep the rows that are not missing. Then we can actually plot it. And then we say plot, and here we call in the plot command again. This basically uses a recipe, and it can just plot automatically. It will find its own backend. And you only need to say plot this geometry and figure out that these are actually points, and we can do that as a scatter plot. And here I see some rough outline, I think, of Europe. This is actually a bug. I think that's the comment I put here, found the bug. They shouldn't be all orange. Funnily enough, the bug is the color bar actually indicates there is a range of data from month, what is it, 1 to 12. But everything is orange, and I'm not sure why. So I can make a bug report later today, or figure it out myself. I did also do a histogram plot of the same column, which we try to visualize. And you'll see there is actually more data there than just the orange part. That it is the peak, but shouldn't happen. Okay, that's it for reading such data. I now read a geo package, but this could be a flat GeoBuff file, a shape file, any of the recent ones. You also have now GeoParquet. I made an implementation of the recent HIP file format. I think Edster is going to present about GeoParquet tomorrow.
Yeah.
So visit his presentation. I really like GeoParquet because it's the first. I think it's the first vector format that by default adds compression to vector data, as far as I'm aware. So it really helped me with storing loads and loads of points. But visit Edster tomorrow for that. Then the last thing I want to talk about is Geo Interface. Because actually what I showed you just now is you have a column with an geometry type. So each geometry here, it does say I'm a WKB point, which is apparently how it's called there in GDAL. But the problem is if you open it like this, you don't know about geometry, right? No one of you does, but to be fair, if I look at it, I also have no clue. It's called geometry. It's apparently spatial. And I can see it's probably a point because it's called points. But I don't know how to get the coordinates out, right? I don't know how many coordinates are actually in there, whether it's 1, 2, 3, or many dimensional. And this happens all the time in the language, because if I make a new package or develop something for my own work, or you do something for your spatial machine learning, and you think, I need a point type. And you make your own struct, you call it spatial, it's a point or something, or you make your own definition of polygon. But others don't know how to access that geometry. It's custom. So one way of now figuring this out is either going to the source code, which is a pain. Well, you can learn something, but it's probably a pain, or hopefully look at some documentation. If you're lucky, there is documentation, well-written documentation. But again, the ecosystem is young. Many developers are really good at coding, and documentation is always lagging behind. So what we try to do is write Geo Interface, and with the idea is that we define a common interface for geospatial data. So we say to package developers, if you implement geometries, spatial geometries anywhere, also implement Geo Interface, because then we have a common interface of accessing coordinates and other information. And this works in a way similar to the plots or to the arrays, which I showed you previously, because the tables, they have a common tables interface. So everything in the Julia ecosystem understands what a table is. Even if they are custom sources, they implement some functions that you can call. And we'll give you the example here. So we say using a Geo Interface, and then we get geom, which is just the first geometry in that table. And it actually helpfully says, apparently the summary, it gives me the coordinates. But of course, this is a string, this description, so it's not good enough. And we can check the type, and if we do question mark geom, doesn't do that. It says no documentation found. But it does tell you this is auto-generated documentation in Julia. It basically tells you it's a mutable struct. It comes from ArcGDAL. It has a certain type parameter. And here we see it. It has only one field in the struct, and it's a pointer. So this points to the GDAL C library, because the geometry is stored in the C part somewhere else in memory. So I cannot work with this. I probably need to find the GDAL C commands to actually get something out. So this is why Geo Interface can come to the rescue, because Geo Interface defines a few common functions, so an API, and you start with is geometry. Well, you could call that on the geometry, and it's just true. So now I'm happy I can use Geo Interface for these ArcGDAL things. And I can call the geom trait, which is the type of geometry this thing is, and it's a point. And I can check the number of coordinates, and I can get all the coordinates itself. and I get them actually as a vector of floats. So now I have a Julia array of these coordinates, and I've gotten them from the C library, all without knowing how GDAL or the C library works. For those familiar with vector data, and I think many of you will, this is based on simple features. So simple features defines number of points, number of coordinates. Sometimes it's a bit fake because there are like 3 types of coordinates. We simplified it a little bit. And we also said, yeah, you can call number of points, and we simplified that to number of geometries. So you can always call n-geom for the number of geometries. And the polygon would consist of line strings, and line strings consist of points. So it's a whole hierarchy that you can traverse. And yeah, I say that's it. Of course, this is a very simple thing. This is only a point. You can go to a multi-geometry and get all the coordinates from it, which is a very long, deeply nested array. But you can still get all the coordinates easily. And this is not only implemented for ArcGDAL, which implements GDAL. This is also for GEOS. This is also for many custom packages in the ecosystem. Also for our native spatial packages that do their own spatial intersection. And Geodata Frames actually works with this. So the Geodata Frames package that I just showed, it basically, if you want to write a geo package, it just takes a table with a column that supports Geo Interface. And then it knows how to actually get all the points out, create GDAL geometries from them, and then save them with GDAL. So this is how we try to combine the whole ecosystem. This is not new, by the way. I believe in Python you have the Geo Interface definition, which is based, I believe, on GeoJSON. So if you want to exchange geometries in Python, a package should implement, well, sort of GeoJSON exchange format. I think this is slightly better, slightly more expensive also because it's based on simple features, and it's working really well thus far. And in that sense, it's also slightly unique for Julia to do it in this way. I think I have 15 minutes left, so I actually wanted to leave it at this, and I can now answer some more questions or help you with installation problems. So any questions about this?
No, I have a question. So, so this Geo Interface kind of solves the cross-package interoperability for vector data.
Yeah.
Is there something similar with raster data going on?
Not, well, partially, because Geo Interface also defines, let's say, the extent with which work for a raster, and also there's a CRS method in there. But no, not completely. Rasters are in a bit of a difficult position, because what you want to do is implement the array interface of Julia itself. So it behaves as a regular array in Julia. So that's an interface we already implement. But what we're actually missing is the translation of the coordinates. So there's a, like I said, CRS, you have the array, but you're missing is the coordinate transformation. And there we don't have an interface for that, although I think we could easily define a function like this. And we basically, I used affine map, which is the coordinate transformations package in Julia. And I think that's the de facto standard. So we could do it like that. That could work. But good point.
Do these raster packages also handle files that are too large to hold in memory?
Depends on the package. I know ArcGDAL is itself based on disk arrays, so it has lazy access. So it only reads the block that you actually need to read. But of course, this depends on bending or tiling of the dataset itself. Geo arrays, which I showed you in the beginning, it has a masked option that's true by default. So by default, I read everything in and mask out no data with the missing value in Julia. But you can disable that, and then you get a lazy data set that doesn't read any data, only when you access that part of the array.
So does Julia have a missing NA, like R and A?
It has a nothing type. So nothing is what you would give back. Well, if your function ends without returning anything, that would be nothing.
Yeah, that's my point.
And
But I mean,
then you have missing.
numerical value
That would be missing. Yes.
Okay.
So you can make an array with one and missing, and then the result is that you get a vector, and the type of the vector is a union between missing and the int64.
That's good.
Yeah.
So this is this is built in. Yeah.
What would like happen if you tried to sum that? Would it calculate it as one? Would you calculate it as missing? And can you adjust the behavior of that?
So missing times anything is also missing. So
Like you
it
sum
propagates.
up the array, though.
Sorry?
If you sum up the array for the vector,
Just do it. Just
yeah,
you got an error. You get missing. And what you can do is do a skip missing, which iterates over it, and then you do get one.
Okay.
Yeah. And what actually in the vector part, I actually showed this because when reading data and it detects it, there are no data values. It's missing in this table, not in the rows and columns that are displayed here, but I had to filter it with this command, with the is missing command, just like you have is nothing in Julia. So that's really helpful. Although to be fair, it's really good that it's in there because otherwise it's ill-defined what you have in other languages. But working actually with this array, this can be painful because many packages implement, let's say, a function that accepts an array that's like this. But if you then put into an array with missing and put it to that function, then the function will complain. So many people assume that there's no missing data in the input of functions. Of course, this is again an ecosystem problem, and this will fix itself over time.
Well, yes, but no, and it's also a problem of R and only, for instance, all the linear algebra routines should take twice as long because every number you have to check whether it's an NA or not. Right, so the missing is not a special value like NaN, which simply passes through the CPU like a normal number.
True.
It's a special flag. So it's a special flag. You need to special case it anyway if you want to propagate it. So in any ecosystem where you have NAs like R, there's a large cost to it.
True that there is a cost to this as well.
So it's probably not going to happen for the the atmospheric chemists and so on. The climate people are not going to propagate in missing values.
No, they probably just do none. Yeah, but they like that more. So that's the flow.
It's a different thing.
It is a different thing. Yes, I agree. I hope we can get to missing, but it means that people will need to write code that uses skip missing and does these checks at least in some stage. But at least it's built in, and it uses the type system. So we have the tools to actually work with it. Any other questions?
Can you show how to convert an array into a JSON string, for example, or GeoJSON string?
There are many ways of doing that, and I didn't prepare this. But normally what you do is either go to the GeoJSON package, or go to one of the many JSON packages that there are in Julia. What's both very useful of Julia, but also at the point maybe a bit of a drawback, is that there's many packages and there's no one holy grail package. I think Julia also doesn't really need it because of these interfaces that they can work together. But it also means there's now JSON 3, which is the latest iteration, of the greatest iteration of a JSON package. And that would be.
But you could do Geodata Frames, right?
Well, that's true. I can go back to the. That was this one, right? Um, ugh. We're improvising. This? That's not what I said.
Yes.
Ugh. Yeah. Geom columns with an underscore. Like this. This is what I love. This is, by the way, not supposed to happen. We can support missing data in Geodata. I'm gonna get back to you and I will show you a few examples, just like the user-defined directory. But I can write GeoJSONs and also JSON strings, but it depends on the use case for which package you would choose. Okay. Any other question before I need to start hacking away at these questions?
Maybe interpreting error messages, because that's something that took me a lot of time when I learned Python initially to sort of understand what the error messages really wanted me to. Are there any tricks or things to about them?
I'd say it's in flux. I think Martijn just suggested to me to use a package called abbreviated stack traces. It's not as bad as Java. But what can happen, because these packages can easily interact, because things can just propagate if they define a certain interface. Sometimes you get an error message and it traces it back through all the packages in the ecosystem. And then you get a really weird error that's, I think, stack trace of 30 or 50 times deep. That can happen. And this one is actually, I'm not sure how long this one is. See, this is, well, 11. So on the replicator, this is actually now not colored, only, well, I think it's trying to parse it as Markdown or some other language that this is now red. But the coloring in the replicator in the terminal is really different and often way better. And that really helps. It also helps with errors you get from package incompatibilities. So we're trying to do a lot with highlighting to show which part are useful and which ones aren't. But we're clearly not there yet. I think this is quite direct and quite good. Although, yeah, if you don't know what an ArchGDL OGR field type is, because we're deep into the C library, that doesn't help. But this is getting harder if you go down. And this is the worst, because this is the combination of the whole data frame with all its types. So what the pull request that which I just talked about, abbreviated stack traces, it's going to try to hide at least all this, unless you specifically ask for it. Because if you see such an error as a new user, it's just help, and you run away. I think this is fine, by the way, because it also, I think this does highlight, by the way, the types that are in place. So this can be a bit helpful. But normally I don't develop in Jupyter notebooks.
What do you use as development environment?
I use Visual Studio Code.
Uh-huh.
And then basically with a terminal next to it. So you do just like actually here, Shift Enter, you execute that line in the, oh, I'll actually show it to you. I need to make this really big, I guess. Oh, a bit small. So this is probably what you're familiar with, at least also in other languages. It's just starting my Visual Studio Code and it's loading a lot. But basically what it does, it's on the left-hand side, you have the source file, extension.jl. And if I do Shift Enter, you got a round thing. Now it's a check mark, so it's actually executed in the replicator on the right-hand side. And this works also as standalone version. And if you execute, you can do. And this has 2 here. So you got that all the way down here. So this is a really interactive way of developing. And this can also work with packages. Because normally, this is now a single script file, but normally I'm developing inside a package. And that's also what Visual Studio Code supports. If you're doing package development, by the way, in Julia, I really advise the package revise. What that does is any change to the package, it will basically hot reload the package. Otherwise, you basically have to restart your Julia session to load the package again, because it tries to compile the thing, and that's why it doesn't reload it. So for package development, revise is essential. And this Visual Studio Code with the plugins, it has autocomplete support, it has the help function built in, can install packages for you. There should be plot panel. Because I don't have that much resolution here on this size. You also have the workspace with the current variables. You can debug in here if you want. There's a plot navigator, so the plots also show up there. So there's a good Visual Studio Code integration. So yeah, this is the best. I think this is the best development environment for Julia. But that's a personal opinion. Before there's Atom before, although I believe Atom is now sort of discontinued, although there will be open source developers who continue using Atom. And I know people are using just VI or the improved version of it. There's also Julia plugins for that, but I think Visual Studio Code one is the most mature. I guess you are not using Visual Studio Code.
It's an age thing.
Okay, any other suggestions, remarks? Because then I think we can call it quits. It's 3 before 5. So it's time to have some drinks and take a swim, I guess.
Thanks a lot.
Thanks. Can I do stop share?